Introduction of two-dimensional spectroscopic method. In one-dimensional experiment, the signal is represented as a function of single parameter, usually the chemical shifts. In two-dimensional experiment, there are two coordinate axes. Generally, this axis also represents ranges of chemical shifts. The signal is represented as a function of each of these chemical shift ranges. The data are plotted as a grid. One axis represents one chemical shift ranges, the second axis represents the second chemical shift range, and the third dimension constitutes of magnitude of the signal. The result in the form of counter plot, where counter lines corresponding to the signal intensity. In a normal pulse NMR experiment, the 90-degree excitation pulse is followed immediately by a data acquisition phase, in which the FID is recorded and the data is stored in the computer. In experiment that uses complex pulse sequence such as depth, a preparation phase is included before the data acquisition. During the preparation phase, the nuclear magnetization vectors are allowed to process, and information may be exchanged between the magnetic nuclei. In other words, a given nucleus may become encoded with the information about the spin state of another nucleus, which may be nearby of the many types of the two-dimensional experiment, to find the most frequent application. Today, one of the important topic of the discussion is today NMR spectroscopy technique. In that we will see different type of the techniques which is used in today NMR spectroscopy technique. That is COSY, correlation spectroscopy, HSQC, Heteronuclear Single Quantum Coherence Spectroscopy, HMBC, Heteronuclear Multiple Bond Correlation Spectroscopy, NOESY, Nuclear Overhauser Enhancement Spectroscopy, ROESY, Rotating Frame Overhauser Effect Spectroscopy, HOESY, Heteronuclear Overhauser Effect Spectroscopy, TOCSY, Total Correlation Spectroscopy. COSY, that is correlation spectroscopy. It is the today NMR spectroscopy technique in that identify which proton in the molecule are coupled to each other. How it works? COSY runs decoupling pulse along the entire frequency range and record all couplings. The resulting spectrum shows cross peak between the protons that are coupled, usually up to 4 bonds apart. What it shows? The peak along the diagonal are the projection of the one-dimensional spectrum. Cross peaks are symmetrical about the diagonal. The magnitude of the coupling affect the peak intensity. How it used? COSY is useful for the determining the coupling between nuclei that are connected through 1 to 3 bond length. A COSY spectrum is an proton-proton correlationship with the proton NMR spectrum plotted on the both axes. It helps to confirm that we have the made right assignment for the coupling of neighboring protons. For the better understanding of COSY experiment, we are taking one of the small example of 2-nitrophenol. In this spectra, 2-methyl group is coming at the doublet at 1.6 ppm, showing as a counter, and second counter of CH group is at 4.7 ppm. Both X and Y axis is represented as a proton scale. Diagonal peak is showing as a self counter and cross peak showing as a proton-proton correlation. So here both methyl group is given as a correlationship with the CH proton. In second example, we are taking COSY spectrum of isopentyl acetate. Here diagonal peak is showing self counter and cross peak is showing proton-proton correlation. Here we are giving the numbering of proton group. In that we are clearly seen group 1 is given correlationship with group 2, group 2 is given correlationship with group 3, and group 3 is given correlationship with group 4. This information is very useful for the finding of correlation at the time of structure confirmation. HSQC, that is Heteronuclear Single Bond Quantum Coherence Spectroscopy technique, is the NMR spectroscopy technique that record proton and carbon chemical shifts simultaneously. It's often used to analyze complex mixtures and especially important in the protein NMR. How it works? HSQC couple proton nuclei with other NMR active nuclei that are directly bonded to them. It uses magnetization transfer to increase the sensitivity of the secondary nucleus. What it shows? The resulting spectrum is two-dimensional with one axis for the proton and the other for the heteronucleus, usually carbon or nitrogen. Cross peak shows which proton is attached to the which carbon atom or heteroatom. What is used? For the HSQC is used to determine the proton to carbon or heteroatom single bond correlation. It's used to confirm the presence of the range of the substance in the complex mixture. When it is useful, HSQC is more sensitive than depth, so it may be more advantageous to use the complex situation. Who discovered it? Geoffrey Boden-Hussein and DJ Rubin first discovered the HSQC technique in the 1980. In this slide, we are observed simple HSQC spectrum of 2 nitrophenone. In that, upper side is carbon scale and B side is the proton scale. In this data, we will clearly see 2 counters. In that, first one is CH3 group showing carbon value at 22 ppm and proton value at 1.6 ppm showing a counter. Second counter is showing CH group at its carbon value at 77 ppm and its proton value at 4.8 ppm. In this slide, we will take second example of HSQC spectrum of isopentyl acetate. In that, we will give the numbering in the structure. So, in that, number 1 CH3 group is given correlation in the form of counter denoted by 1 at 0.9 and 24 ppm. Similarly, all other group is showing a similar counter. From this, we will clearly understand the proton and its carbon correlation. It is very useful in the structure confirmation. In this slide, we will take third example of HSQC spectrum. It will help to deeply understand our HSQC knowledge. So, in this spectrum of 4-methyl-2-pentanone, 3CH3 group is given 3 counters at different position. Second important observation is CH2 group is splitted in the proton scale, showing single proton and its carbon scale is same. Hence, we will clearly understand their correlation. HMBC, that is Heteronuclear Multiple Bond Correlation Spectroscopy technique, is an important NMR experiment that helps to determine the structure of the organic molecule by showing how protons are related to carbon and other heteronuclei. What it does? HMBC correlates protons and carbon through 2, 3 or sometimes 4 bonds. It provides 2D correlations map between the long-range coupled proton and heteronuclei, usually carbon. What is used? For HMBC is the key tool for the illustrating the structure of the complex organic molecule, peptides and natural products. How it works? HMBC spectra shows proton spectra on the x-axis and carbon spectra on the y-axis. A cross peak indicates that the corresponding protons and heteronucleus are 2 or 3 bonds away. Limitations: HMBC can't distinguish between 2 bonds and long-range correlation. This can lead to ambiguities in the structure elucidation. HMBC experiment gives correlation between carbon and proton that are separated by 2, 3 and sometimes 4 bonds in conjugation system. Direct 1 bond correlation is suppressed. Quaternary carbon's atom will be detected. The intensity of cross peak depends on corpuscle relation for dihedral angle near 19 degree. The coupling is near 0, thus the absence of cross peak. Here we will see HMBC spectrum of ethyl benzene. In this spectrum, we will clearly show that quaternary carbon is given third bond correlation with C3 carbon and C8 carbon. It will be easy to find out correlation and confirmation of the structure. In this slide, we will see both HSQC and HMBC spectra of one compound and see the difference between them. So in HSQC, blue color counter showing CH and CH3 group, that is odd number of proton attached group, and the red color counter shows CH2 group, that is even number of protons attached group. In HSQC, we will find out which proton is directly connected to which carbon atom. In second spectrum of HMBC, we will see second bond and third bond correlation. So in this spectra, some counters are dark color and some counters are faint color. So in that we will only see dark color counter, that is the third bond correlation counter. NOESY, that is Nuclear Overhauser Enhancement Spectroscopy, is the two-dimensional nuclear magnetic resonance spectroscopy technique that provides the structure information about the molecule. How it works? NOESY saturates nuclear spin and observe changes in the intensity of nearby nuclear spin signal. What it shows? NOESY shows through the space interaction within a molecule, which help to determine the molecule in the steady structure. What is used? For NOESY is the key tool for the determining the stereochemical relationship in the molecule and is useful in the chemistry, biology and physics. For example, it can predict a molecule reactivity or determining if two molecules are interacting in a biological system. Whereas COSY generally correlate proton view geminal or vicinal scalar spin coupling, or NOESY shows correlation of protons that are spatially close no matter where they are as well as close through bond and therefore scalar coupled or not. The interaction that is important for an NOE transfer is so called as dipole coupling, which can be directly observed in the solid or partially oriented phases. However, the NOE also leads the intensity changes of the signal. The signal that are coupled proton is saturated. This effect is based on the relaxation behavior and it can lead to a signal enhancement as well as to the signal reduction. ROESY, that is Rotating Frame Overhauser Enhancement Spectroscopy, is the two-dimensional nuclear magnetic resonance spectroscopy technique that helps to identify which signals come from protons that are close together in the space. How it works? ROESY is the type of nuclear overhauser spectroscopy technique that uses the rotating frame of the reference to the enhancement, the detection of the nuclear overhauser effect. When to use it? ROESY is useful when the noisy signals are weak, such as when they are in the near transition between the negative and positive. It also used for the molecule with the molecular weight around the 1000. What it provides? ROESY provides through the space correlation view the rotation nuclear overhauser effect. It can also distinguish between the true NOE signals and exchange peak in the large molecule. How to interpret the spectrum? In ROESY spectrum, cross peak indicates the spatial proximity and the spectrum is symmetrical about the diagonal. In this slide, we will see one of the example of two-dimensional ROESY. This technique gives information about the space-through correlation in three-dimensional structure of all protons in our structure. This technique showing a proton-proton correlation of space-through up to 5 angstrom. In this example, nitrogen attached CH proton correlate with CH2 protons, indicate for the formation of imine group. Such correlation formation means that cis isomer is the major one. HOESY, that is Heteronuclear Overhauser Enhancement Spectroscopy technique, is the nuclear magnetic resonance spectroscopy technique used to study the interaction between the different type of the atomic nuclei in the molecule. How it works? HOESY measures the enhancement of the molecule spin relaxation to study the interaction between atomic nuclei. It's a dipolar coupling based experiment that uses a 2D map to show cross peak between the nuclei. The intensity of the peak indicates the distance between the two atoms, which help to chemists determining the molecular structure. Application: HOESY is used to probe intramolecular contact between the small molecule system like ionic liquids, surfactant micelles, metal organic framework, and nucleosides hydrate. Comparison to NOESY, HOESY is similar to NOEs, but HOEs are weaker than NOEs. HOESY also used to different type of the interaction than the COSY, which used as J coupling interaction between the protons. HOESY is also known as 19F HOESY. Many of you use proton noisy spectra to establish whether or not two types of protons are close together in the space. The same type of experiment is also possible between two types of nuclei of different isotopes. This technique is called as HOESY, that is Heteronuclear Overhauser Effect Spectroscopy, and can be used to access the spatial proximity between two heteronuclei. Below is an example of fluorine detected fluorine and proton HOESY spectrum of sugar. In this slide, we will see today HOESY spectra of the molecule A and B. Correlation between NH and CF3 is evidence the detection of strong cross-peak. In this example, we can clearly see CF is came at -129 ppm and CF3 is came at -61 ppm. From this, we will get help to find out the difference between CF and CF3. TOCSY, that is Total Correlation Spectroscopy, is the type of 2D NMR spectroscopy technique that establishes correlation between the all protons in the spin system of the molecule. What it does? TOCSY creates correlations between the protons that are not just geminal or vicinal like in a COSY, but can be distinct as long as there is the coupling between every intervening protons. How it works? TOCSY adds the mixing period of the pulse sequence of COSY, which allows the magnetization to be transferred from the one spin to the next throughout the entire spin system. What it shows? TOCSY spectra shows cross peak for all protons that are the part of coupled spin network, displaying the entire chain of protons. What is used? TOCSY can help to identify discrete building blocks within the molecule or distinguish spin system from the different molecules. What is useful? TOCSY spectra are the phase sensitive, which tends to provide higher resolution spectra with sharper peak. A COSY generally correlate proton view geminal or vicinal scalar spin coupling. A TOCSY can yield correlation of complete spin system. Spin system are a group of protons within a molecule that are within an uninterpreted chain of adjacent proton. Only quaternary carbon atoms or heteroatoms without directly bonded proton or with exchangeable protons will interpret this spin system. This means that the TOCSY can help drastically with the assignment of groups. For example, on peptides, a TOCSY will yield a subspectrum of the every amino acid in the row. In this slide, we can see the difference between TOCSY and COSY spectrum of 3 leptonon, whereas COSY gives relation to the only that proton that are directly attached to the proton by cross peak and diagonal peak as showing as a self counter. In TOCSY spectrum, diagonal peak shows a self counter and cross peak shows the total correlation, that means directly attached to the proton and space through attached proton also. At the end of two-dimensional spectroscopy, we would like to say thanks to my supporter, my family and all of you, giving the best wishes for the study of NMR spectroscopy. Happy New Year to all of you.